Okay, good morning, class. So, as I discussed during the last lecture as well, that we'll be having our final exam next Monday. So today's Wednesday, so I'm talking about the next Monday. So this weekend, after this weekend, and in that final exam, the topics that we'll be covering are MOSFETs and BJTs. Of course, so MOSFETs, what we have covered, and MOSFETs are of course the most important one out of those two. So whatever we have covered in class, that includes the DC and AC analysis of MOSFETs, different kind of amplifiers such as common source, common gate, and common drain amplifiers, differential amplifiers, and op amps. So those are the most important topics for you for this final exam. So in terms of the homeworks that we have covered, so those are basically your homework number 5, 6, 7, and 8. So if you wanted to quickly review all the topics that we'll be covering for the final exam, those will be the topics that are there in homework number 5, 6, 7, and 8. So if you're studying those 4 homeworks and all the topics related to that well, you should not have any trouble in the final exam. All right. Now, officially, the syllabus is up to lecture 35. So that is whatever we had covered till Monday's lecture, except for the CMOS logic. So we started with CMOS logic. That is basically the digital logic. How do you implement digital logic with transistors? That is something that will not be part of your final exam. Okay. So it's only MOSFET based analog circuits involving amplifiers that can include common source, common gate, common drain, as well as differential amplifiers and op amps. Of course, the current mirror is also part of it, which was your homework number 7. All right. Any questions on the final exam? Okay. If not, let's start with our regular discussions on the CMOS logic that we started during the last lecture. So what you looked into in the last lecture is basically if you have, let's say, a common source type amplifier, that you have this transistor over here, you have a load, and you already know how to analyze a common source amplifier, how to analyze its DC biasing points, how to analyze its AC gain, and so on. You have also looked into VTC, the voltage transfer characteristic, that is V out over V in of this amplifier. And remember that V in is applied at the gate. So that's the V in that you are applying here, and V out is taken at the drain of this common source amplifier, right? Now, one way to graphically solve these kind of amplifiers is that you draw the characteristic of the device. That's your MOSFET over here. So you draw the ID versus VDS characteristic, or I out versus V out characteristic of the MOSFET, and you draw the load line for the resistor. So you already know the concepts of load line, you already know the concepts of output characteristic of a device, and the point where they intersect, where the point where the load line and the output characteristic of the MOSFET intersect, that's basically the operating point of your system. As you change the value of RL, this load line will move. If you change the VGS of the MOSFET, the output characteristic will move. So for example, this line is corresponding to a low VGS. Gate to source voltage is lower. That's why your ID current is lower. On the other hand, this curve corresponds to a high gate to source voltage. And that is the reason why your current ID is higher, because ID is nothing but K times VGS minus VT whole squared. If your VGS goes higher, the current will also be higher. So these curves that we are representing over here, so this is for a low VGS, and this is for the highest VGS that you are applying in this circuit, right? So that's why you have these multiple curves. So now, of course, depending on the VGS that you are applying, the intersection point of your load line and these output characteristic of the MOSFETs will change. Let's say you have a very, of course, if you have a very low VGS, if you have this very low VGS, that means you are at this curve, right? You are following this curve. And the intersection point of the load line and the characteristic of the MOSFET is at this point. And remember that this intersection point is basically giving you your operating VDS, that whatever drain to source voltage you have for this particular MOSFET, right? Similarly, if you move to this point, which is basically at a higher VGS, that means a higher V in. But as you see that this intersection point is moving left, right? As you go to higher and higher V in. So as you go to higher V in, this intersection point is moving towards left, which means that the VDS or the V out is actually reducing. And that's what is given by your VTC, your voltage transfer characteristics. That as you increase your V in, your V out reduces. Right? So that's another way of understanding the VTC, which is graphically, that as you are increasing your input voltage, your output voltage reduces. Of course, there would be a region when your output voltage does not change over here. That is, you have a VGS so low that you do not have any kind of current flow through the device. So that is basically corresponding to a VGS where your output characteristic is kind of superimposed on top of the x-axis. So if you have a VGS which is extremely low, that is below the cutoff of this particular device. If gate to source voltage is less than the threshold voltage, the device will be in cutoff region and there will be no current flow. So your current will be corresponding to the x-axis. And at that point, what would be the intersection point of your load line and the x-axis? That is this point, which is equal to VDD. And that's why your output voltage is equal to VDD when you are in cutoff. And then as your device turns on, as you apply more and more input voltage, your output voltage keeps on reducing because this intersection point that keeps on moving towards left, right? As you increase your VGS, your curves go up in this direction. So the intersection point of the load line and those curves will move towards left. And that's what is given by this part of the VTC, where as you're increasing your input voltage, your output voltage reduces. And then there comes a time when you go into triode, when you're not in the saturation region anymore, you go into the triode region, which is here, here, or here. So at that point, you'll see that the output voltage will become very close to zero, because in triode, this is what your VDS or your output voltage is. For example, if you're at this point, this much is your output voltage, which is very close to zero, right? So when you go to triode, your VDS of the device becomes very low. And that's also from definition, that what is the definition of your triode region? The definition of the triode region is that VDS is less than V overdrive. So if the VDS is low, it's even lower than the overdrive voltage, which is VGS minus VT of the device, then you are into triode, which means that your output voltage or VDS is very low in the triode region, which is determined or which is indicated by this region in your VTC. So if you're talking about digital operation, you are interested in either the cutoff region when the VDS of the device is very high, or in other words, the device is off. Okay, so the device is off when the device is in cutoff region, or when the device is fully on, when it is in the triode region. And when the device is in the triode region, your triode, the VDS or the drop across the device will be very small. It will be almost very close to zero. That's in this region where the device is in triode, right? So the drain to source voltage is small in that case. And if the drain to source voltage is small, which means the drop across the device is small. Now you know what is the property of an ideal switch, that if the switch is open, you have infinite resistance from the switch. It's an open circuit. If the switch is open, the circuit is open. That means the resistance of the switch should be infinitely large. That's what will happen when the device is off. When it is in cutoff region, there will be no current flow through the device. So the resistance is close to infinity. You can say it's very large. So that's what is meant by the switch is open in terms of digital nomenclature. And when the switch is closed, let's say when the switch is closed, at that point, ideally, you would want a short circuit. You would want zero resistance between the two terminals of the switch when the switch is closed. So if you have a short circuit, what is the voltage difference between the two terminals of that short circuit? The voltage difference should be zero. That's why it is called a short, as the voltage is the same on the two terminals. That can only happen if the VDS of the device is very small. In other words, when you are in the triode region. So if the device is in triode, you have a closed switch. When the device is in cutoff, you have an open switch. When the device is in saturation, you have an amplifier. So those are the physical significances of the different regions in a VTC. That here, you have an open switch. Here you have an amplifier. Here you have a closed switch. Okay. So in terms of digital operation, you're interested in either the cutoff region or the triad region. That is when the switch is off or when the switch is on. That's why it's called digital. It's on or off. On the other hand, when you're talking about analog properties of the device, you're interested in this region, which is basically your saturation. So if you are building an amplifier, you need to bias the transistor in saturation region. If you are building a switch, it needs to be in the cutoff region or the triad region. All right. So this cutoff region, for this cutoff region, what is the boundary of the cutoff region? The boundary of the cutoff region is up to that point. So if your Vin is less than the threshold voltage of the transistor, you're in the cutoff region. So that's when your output, let me clear this up a little bit. So that's when your output voltage is equal to VDD because the switch is off. So all the voltage drop is happening across that off switch, which is an open circuit. So the VDS of the open circuited switch or the open circuited MOSFET is equal to VDD. So below your threshold voltage, so remember that your x-axis is your Vin. So when your Vin is less than the threshold voltage, your output is equal to VDD. After that, the device turns on and the device turns on in saturation. So when your device turns on from the off state, it always turns on in saturation. Why is that? Because they can remember that what is the definition of saturation region? The definition of your saturation region is that your VDS is greater than V overdrive. Okay, your VDS was already very, very high to start with. Your VDS was equal to your VDD or the supply voltage in this region. Now, why the device was cut off? That was because your overdrive was less than zero. Your VGS was less than the threshold voltage. Now, as soon as your VGS crosses the threshold voltage, you have a very small but positive V overdrive. Your VDS was already at VDD. Your V overdrive is probably 1 millivolt or 10 millivolt, maybe 100 millivolt. Whereas your VDS was 5 volts if VDD is equal to 5 volts. So which means when the device turns on, it turns on into saturation region. So from cutoff directly to saturation, that's how it goes, right? So there is no triad region in between. Actually, the triad region happens when you have a very high VGS. So if your VGS keeps on increasing, that means your overdrive keeps on increasing, but at the same time, your VDS keeps on dropping. Your VDS keeps on reducing according to your VTC, voltage transfer characteristic, right? So there would be a point when your VDS will drop and your V overdrive will increase to such a value that your VDS will become lower than your V overdrive. And that's the point when you will enter the triad region, which is after this point. So that's again a graphical explanation of how your VTC is found from the characteristic of the MOSFET and the load line. Okay, so that's about digital versus analog. Now, if you're asked to design any kind of digital circuit, let's see how we can do that. So one of the most or simplest or easiest to design digital circuit is the inverter. The meaning of an inverter is that whatever digital logic you'll have at the input, you'll have the inverted digital logic at the output. So that's why it's called an inverter. The symbol for this inverter is this, that you have this triangle followed by this circle. This circle is very important because if you don't put this circle, it means that it's not an inverter. It actually means a buffer, which means that whatever is your input will be equal to your output for a buffer. For an inverter, whatever is your input, output will be opposite of that. So if your input is 0, a digital 0, your output will be a digital 1. Now, you may ask, what is the digital 1? A digital 1 is just a high value in terms of voltage. So you can define two levels in an analog world that, okay, I'll consider only 5 volts and 0 volts. So I'll consider only my VDD or I'll consider only the 0, right? So you can define your own logic high and logic low, depending on your circuit. So your logic low is usually the 0 volt or the ground. Logic high could be as high as your VDD. Let's say if your VDD is 3.3 volts, your logic high is 3.3 volt, which means the digital 1 represents 3.3 volt. If your VDD is 5 volt, logic high will mean 5 volt. So that's it. But logically, it represents a higher value. That's why it's called 1. So if your input is 0, output is 1. If your input is 1, output is 0. So how do you actually build an inverter? So to build an inverter, what you really do is that, and the logic function for an inverter, let's call the output as Y and the input as A. So the logic function of an inverter is represented as Y equal to A bar. So the A bar says that if your input is A, if your input is 0, your output Y will be 1. So that's what is indicated by this bar. Now, how to draw the equivalent digital circuit for this using MOSFETs. So for that, what you'll consider is, first of all, you have to start with Y bar. Okay. So this is the next what I'm going to talk about is how to design any digital logic from a function. If you're given a function, how to define or how to design the MOSFET-based circuit for that function. So if your function is Y equal to A bar, you have to start from the point that you need to find out what is Y bar. And Y bar will, of course, be equal to A, right? Now, the way you'll design the circuit is that you'll design this Y bar first. So Y bar, what does Y bar mean? Is that what is the reverse logic of your function? What is the opposite logic? That if what is the value when your logic value is equal to 0? So Y bar means that you're trying to find out when your logic's value is equal to 0. Logic's value is equal to 0 when your input's value is equal to 1. In this case, what this means is that your logic's value is equal to 1. So Y is not inverted. Y, there is no bar above Y, which means that you're looking at the logic value when the output is high. Output is high when the input is low. On the other hand, here, the output is low when the input is high. So when you're designing any function, you'll start from the point when the logic value of that function is equal to 0. Okay, and I'll tell you why you would want to do that. So if you are doing this, that you start from Y bar, which is equal to A, so you first draw a NMOS and connect the source of the NMOS to ground and the gate of that NMOS to whatever value you have on the right-hand side of your function. So in this case, it's just A. And you'll connect your output at the drain of this NMOS. So your output is Y, and I'm drawing a capacitor just to hold that value of the output. So generally in digital circuit, the load is a capacitor, not a resistor. And that is because all MOSFETs will have some parasitic capacitances. So if there is a MOSFET following this particular device, then you'll see a parasitic capacitive load. You will not have a resistive load. You will see a capacitive load, and that will be defined by the parasitics of the device. In most cases, you can also have a physical capacitance, but that's rare. Okay, so that's how we are designing a part of the circuit. That okay, you design what is Y bar. Why we are calling this Y bar? Because remember that when your A is equal to 1, when the value of A is high, what will happen to this MOSFET? The MOSFET will turn on because the source of the MOSFET is grounded. The gate of the MOSFET is connected to A. When A is logic high, when A is 5 volts, what is VGS? VGS is 5 volts, right? Gate is at a higher potential, source is at 0, so the MOSFET will turn on. What will happen if the MOSFET when the MOSFET turns on? And remember, when we say the MOSFET turns on, we mean that the MOSFET is in triode, that it works as a short-circuited switch. Right? We are talking about digital circuits now. So when the MOSFET is on, it works as a short-circuited switch, which is in the triode region. So when it is short-circuited, which means that the drain to source voltage of this MOSFET is almost equal to 0. Also, in other words, you are shorting this output to ground, or whatever charge that was stored in the capacitor that gets shorted to ground. So your capacitor actually discharges. So your output will become 0. So now you see why we design or why we put an NMOS over here. That whenever your right-hand side of the function becomes 1, the output of the function becomes 0. So that's why you try to design Y bar first. That you are trying to design when the output of the function becomes 0. If you try to design Y, then you are trying to design when the output of the function becomes 1. Y is equal to something. That means when that something becomes true, Y will become 1. Here, Y bar equal to something. That means when that something is true, Y bar will become 1. In other words, Y will become 0. Right? So that's why you always start with this y bar. Not if your given function is y, you start with y bar and design the NMOS based circuit according to it. That you put that NMOS based circuit over here. In this case, it's just one single NMOS. The output is connected at the drain and the input is at the gate. So this is called the pull down network, or PDN, pull down. So you're pulling down the output voltage. That's why it's called the pull down network. Okay. You also need to design something called a pull up network. And we'll come to that what is a pull up network. The pull up network actually defines that how your output capacitor will be charged. And right now we just talked about when it will be discharged. But to discharge something, it needs to be charged in the first place. So how does this capacitor get charged? The capacitor gets charged through a pull-up network, or something that pulls up the voltage of that capacitor. What would be the pull-up network? The pull-up network will just be a dual of whatever you have drawn here. So in this case, you have drawn an NMOS. For the pull-up network, you'll draw a PMOS, because PMOS is the dual of the NMOS-based circuit. You'll connect the drain of the PMOS to the same drain of the NMOS. You'll connect the source of the PMOS to VDD. And you'll connect the gate of the PMOS to the same voltage that the gate of the NMOS was connected to. So that gives you a CMOS inverter. Now, how does this work? Let's just try to analyze it a little better. That when A is equal to 0, what is happening to this circuit? So the gates of both the PMOS and NMOS are equal to 0. The source of the PMOS is at 5 volts because it is connected to VDD. The source of the PMOS is connected to 5 volts. Maybe let me draw it in a separate location so that it's easier for you to understand. So what you drew in the last page is basically this PMOS followed by this NMOS. The source of the NMOS connected to ground. The source of the PMOS connected to VDD. The output is taken from the common drain, or the drain that is common to both of them. And you can connect a capacitor to indicate that it is the load. The input is provided to the gate of both of them. So this is your A and this is your Y, right? So this is the circuit we had drawn. And we are saying that Y is equal to A bar for this. So why is that? So let's just assume your A is equal to 0. When A is equal to 0, what is happening? That the gates of both of these transistors are equal to 0. So if the NMOS's gate is equal to 0 and source is equal to 0, is the NMOS on or off? Off, right? Because gate is at 0, source is at 0. So the NMOS will be off. So it will be open circuited. On the other hand, for the PMOS, the source is at VDD. Source is at VDD, gate is at 0. So what is VGS? VGS is equal to minus VDD. So the PMOS is on. In other words, VSG of the PMOS is equal to VDD, which is larger than the threshold voltage of the PMOS. So if your VDD is more than the threshold voltage of the PMOS device will be on. So now you see that the NMOS is off. That means the NMOS is open circuited, but the PMOS is on. So it will charge through this path. The capacitor, the output capacitor, will charge through the on PMOS. And the output will become Y equal to 1. So when your input equal to 0, output is equal to 1. On the other hand, when your input is equal to 1, what will happen is that this PMOS will turn off, because now for the PMOS, your source is at VDD, the gate is at VDD, because remember 1 is equal to VDD in terms of analog voltage. So if your source is at VDD, gate is at VDD, what is VSG for the PMOS? 0. If VSG is 0, PMOS is off. It is less than the threshold voltage of the PMOS. So your PMOS is off, but on the other hand, your NMOS is on, because the VGS of the NMOS is equal to 1. So if your NMOS is on, this will discharge, the capacitor will discharge through this path. So your output will become 0. So as you see that when your input is 0, output is equal to 1. When your input is 1, output is equal to 0. So that's how we design a CMOS inverter. But using the same logic, you can design any function in the world. Okay, so let's see how you're going to do that. So let's say you want to design a NOR function. Okay, what is a NOR gate? The truth table for a NOR gate looks like this: that if A and B are two of your inputs, the output of the NOR gate will be equal to 1 only when the inputs are both 0. The output of the NOR gate will be 0 when any of the inputs is 1 or both the inputs is 1. That's the definition of a NOR gate. right? So I'm assuming that all of you know what a NOR gate is. It's just an inverted OR. So what is a OR gate? That the output will be 0 when both the inputs are 0. The output will be 1 when any of the inputs is 1. That's an OR gate. The inverted version of an OR gate is a NOR gate. So that's how the truth table of the NOR looks like. So how do you design the NOR gate? What would be your pull down network? So remember, what is the function for a NOR gate? The function for a NOR gate is y equal to A or B inverted. Right? So you have A or B, and then you invert it, you get the function for the NOR gate. What we said is that you first need to design Y bar. It does not matter what your function is. Your function could be anything on the right-hand side. What you start with is what your Y bar is. You try to design your pull down network first. That what makes your output 0. And you'll make sure that that circuit is designed using NMOS. We'll discuss why you want to design it with NMOS as well later. But right now, let's just assume that you design your pull down network always with NMOS and your pull up network always with PMOS if you want to make it a CMOS logic. And why is that called a CMOS logic? Because that's complementary MOS. So what is meant by complementary MOS is that if the pull up network is designed with PMOS, the pull down network will be designed with NMOS in a dual way. So that's why it's called complementary MOS or CMOS logic. Now, what is shown here is not complementary MOS. Here, you have an NMOS in the pull down network. Your output is over here. Your pull down network is this, whereas your pull up network is just a resistor. Okay, so this is not complementary MOS logic. This is just NMOS logic. So this is called NMOS logic, but you do not have a PMOS pull-up network. You have just as a resistor as a pull-up network. So now let's see why this works as a NOR. This works as a NOR because your Y bar will be equal to A or B. So first, you are interested in knowing what makes your output equal to 0, what makes your Vout equal to 0. And if you put these two NMOSes in parallel, when any of these NMOSes are 1, when any of these NMOSes are on, if the gate voltage is high for any of these NMOSes, the output will discharge through that NMOS. So let's just say that the NMOS which is connected to A is on. Then the output will discharge through this path. On the other hand, if the NMOS which is connected to B is on, the output will discharge through that path. And if both of them are on, output will discharge faster through both of them. So that's why you're first designing what is Y bar, what makes the output discharge. And the output gets discharged through this NMOS network. And if any of the NMOSes are on, you'll discharge it because that's what it says, that A or B is your Y bar. So it can discharge either through A or through B. On the other hand, if it is a NAND logic or an inverted AND logic, so in an inverted AND or in a NAND logic, your output is equal to 1 when any of the inputs is 0. Okay, when both the inputs are equal to 1, your output is equal to 0. So that's the definition of a NAND. And the symbol of the NAND is over here. The symbol of the NOR is over here. Remember to put this bubble to put this circle at the output, because without this circle, this one means a OR. And when you put the circle, it becomes a NOR. On the other hand, here, without the circle, this is an AND gate. And with the circle, this becomes a NAND gate. That's how the symbol is. I mean, it's just how you represent the symbol. Now, from the truth table of the NAND gate, you know that when both of these devices are, or both of the inputs are 1, your output is 0. So the definition of a NAND gate is equal to Y equal to A and B whole bar. So you take AND of A and B, and then take a bar, take an invert of that, that becomes a NAND gate, right? Again, I'm just assuming all of you know what a NAND gate is, like by definition. And please let me know if it is otherwise, because then we can go into the details of why you call it a NAND, why you call it a NOR, and things like that. But at this point, I'm just assuming that you know about this. So from the truth table, you again found out that your Y is equal to AB bar. So how would you design the logic is that first, again, you'll start with Y bar, and your Y bar is equal to AB, which means that you have to put these two transistors which are connected to A and B in series. Only when both of them are on, your output will discharge through this path. If any of them are off, your output will not discharge. Right? The output can only discharge if both of these switches are short circuited. If any of those switches are open circuited, the output cannot discharge. There cannot be a path from the output to the ground if any of these switches are open. So that's why you'll put those two switches or those two MOSFETs in series when it is your function y bar looks like this, when it is A times B or A ANDed with B. And A and B will, of course, be provided at the gates. Again, this is a NMOS logic. This is not a CMOS logic. The CMOS logic will be when you put the equivalent PMOS circuit on top as your pull-up network, and that PMOS logic will be a dual of the NMOS logic. What is meant by dual of the NMOS logic? That if your NMOS is in series, your two PMOSs will be in parallel. On the other hand, here, if your two NMOSs are in parallel, the two PMOSs will be in series. So that's what we'll learn next. But before going there, this is the theory of the CMOS inverter. That this is something we already discussed. That why your output becomes your input complemented, the complementary version of your input, and this is what your VTC looks like. Just go through this now. This is the mathematical derivation of your inputs and outputs. So, for example, in the triode region, you already know what is the equation for triode. The equation for triode is ID equal to K times VGS minus VT minus VDS over 2 times whole times VDS. Or you can also represent as K times VGS minus VT times VDS minus VDS squared divided by 2. That's the equation of triode for a NMOS transistor. Okay. So when your Vin is equal to VDD, when Vin is equal to VDD for the CMOS inverter, your M1, which is your NMOS, so this is your NMOS device, has a highly conductive channel. This is in triode because your VGS is very high. But M2, the PMOS will be off. So the ID current through the PMOS will be equal to 0. Because the ID current through the PMOS is equal to 0, the output the output which is here, where you can connect a capacitor, the output is not charged anymore through this path. So this path does not exist when your input is equal to 1. So you can only discharge. Again, something that we discussed before, that you can only discharge when your input is equal to 1. And when input is equal to 0, your output will be equal to VDD. Again, something that we have discussed before. Now, what is the resist? Now, as we were saying, that if the devices are off, you have an infinite resistance because you can assume that it's an open circuit. But when the device is on, it's not ideally it should have been a short circuit, but in practice it is not. In practice, you have some amount of on resistance, and that you can calculate from this equation itself, that your ID is equal to K times VGS minus VT times VDS minus VDS squared divided by 2. So let's just assume that your VDS is very small. You are deep into triode region. So your VDS is very, very small. So in that case, you can neglect this VDS squared term. So this VDS squared term goes away. So what is left with is this ID term on the left and K times VGS minus VT times VDS on the right. What is your resistance? The resistance is voltage, output voltage divided by output current. What is your output voltage? That's equal to VDS. What is your output current? That's equal to ID. So VDS divided by ID will give you the output resistance. And that output resistance will be almost equal to K times VGS minus VT inverted. So K times VDS minus VT inverted, that will become your output resistance. Okay. Now, of course, you may choose not to neglect this VDS squared term, and then you have to solve a second order equation to find out what would be your VDS divided by ID. Okay, and that will look something like this if you solve that second order equation. Okay. So now in a CMOS inverter, what is interesting to see is that when your input voltage is very low, when your input voltage is over here, then your M1 is off, then your NMOS transistor is off when your input voltage is very low. So this is 0. Your NMOS transistor is off. When your input voltage becomes higher than VGS, or when VGS becomes higher than the threshold voltage at the input, then your then your NMOS turns on, and the NMOS turns on in saturation, right? Because as you said that one device will turn on in saturation all the time. But what is happening to the other device? For the other device, the output voltage is still very high. The VDS, the VD is still very high, whereas VS is again very high. This is at VDD. So the PMOS device is still in triode in this region. So in this region, your NMOS has turned on, but your PMOS is still in triode. That's because your output is still very high. Output has not reduced that much. Output was equal to VDD earlier. Now it has reduced by a tiny amount, but not by a large amount. So which means that the VSD of the PMOS device is very, very low. And if VSD of the PMOS is very low, that means it is in triode region. So right after your cutoff region, here your M2 device is still in triode. So this is your M2 and this is your M1. So your M2 device is still in triode. After some more time, both of them will go into the active region or the saturation region, and that's when you see a high amount of gain. So for an analog circuit, that's where you will be interested in. But then again, there would be a region when M1 will go into triode. So M1 goes into triode over here as you keep on increasing your VGS, and M2 is in saturation. And then there would be a region over here when M2 device will become off. So that is the description of all the 5 regions that you'll see in a VTC. That first you'll see a constant voltage over here, then that voltage will start changing, but not much. Then you'll see a large change in output voltage. That's where you get a high gain. Then again, your gain will reduce. That's because one of the devices will go out of saturation. And then one of the devices will go into cutoff. And that's why your output will become flat again. So those are the 5 regions in a VTC for a CMOS inverter. Okay. So now how to design these CMOS logic circuits? You have already looked into this, that for a NOR gate, your function looks like y equal to A or B whole bar. So if you go for y bar will be equal to A or B. So that's why in the pull down network, first you'll design the pull down network and you put A and B, the transistor A and the transistor B, those two will be in parallel, because if any one of them is on, your output will be discharged through that path. So that's why y bar is any one of them becoming on and the output will be discharged. The PMOS logic will be a dual of it. So if your pull down network or your NMOS logic is in parallel, the PMOS logic will be in series. Why is that? Again, you can do a little bit of mathematical manipulation here to understand this better. So y bar equal to A or B. So y is equal to A or B whole bar. Now, I guess most of you know a law called De Morgan's law, and you can prove the De Morgan's law from the truth table, that if you have A plus B whole bar, that is equal to A bar and B bar. So A or B whole bar is equal to A bar ANDed with B bar. So that's De Morgan's law, and you can prove that from the truth table. I'll leave that as an exercise. But now this means that your Y will be equal to A bar ANDed with B bar. That means you have a series operation when you are trying to find out how this output charges. When you are trying to find out what is Y, that means you are interested in how the output charges. When you are looking at Y bar, you are interested in how the output discharges. So how does this output charges? You have to put 2 components in series. You already get a sense of that from the De Morgan's theorem. So you are putting 2 of these components in series, but of course, because this is PMOS, if you put A in the gate of it, you are actually looking at VSG and not VGS, and that's why that bar comes into play. So you do not need to put a bar at the input. If you're connecting A for the NMOS logic, you'll connect the same A for the PMOS logic as well. If you're connecting B over here, you'll connect the same B for the PMOS logic as well. So you can just in a similar way that I described the pull down logic, you can understand the pull up logic as well. What happens for NAND? For NAND, Y is equal to AB bar. So you know that A and B has to be in series, because for the pull down network, you'll be looking at Y bar, and Y bar means you'll have A ANDed with B. So you have A and B both in series, that's your pull down network. Pull up network, just the dual of that. Because A and B are in series, they'll go in parallel with the PMOS based pull up network. Now let's see how do you design a random logic. So let's say your logic is Y equal to A ANDed with B plus C or B or C whole bar. So that's your logic Y. And you can be given a truth table as well. Let's say this is a truth table. From the truth table, you can find out what is the logic. Now to design the CMOS circuit, you're interested in first, what is Y bar? So Y bar is equal to A ANDed with B or C. So now you see that B or C, which means that these two transistors will be in parallel. That gives you the OR operation. And then ANDed with A, that means A will be in series. This transistor will be in series with the parallel combination of these two transistors. So that's how you design your pull down network. What would be your pull up network? Again, just the dual of it. So if your B and C, these two transistors were in parallel before, they will go in series. So as you see here, B and C, they are in series. On the other hand, the transistor for which it was connected to A, that was in series with the parallel combination of B and C. Now the transistor which is connected to A, that will be in parallel with the series combination of B and C for the pull-up network. So it's just a dual of. Again, you can analyze it just the way we analyze the CMOS inverter, and you'll see, and again, I'll leave that as an exercise for you to see that, okay, this really works. Okay. But this is how you'll design. Like you first try to look for what is your Y bar, design your pull down network according to that, and your pull up network will just be a dual of that. Okay. So now what we discussed till now is short circuited switch and open circuited switch. In real world, an open circuit is not fully open circuit. It's not infinite resistance. There would still be some finite resistance. And that's the reason why in real world, you'll see some amount of leakage through the devices. Even if you assume that the circuit is open, there would be some leakage path from, let's say this point is A, this point is B. Your assumption would be that because this switch is open, there cannot be any current flowing between A and B. That's ideal world. In real world, there would be some amount of leakage current between A and B, but that leakage current will be very small. What is more problematic is that when you assume that it is a short circuit, that A and B are shorted, it's not really shorted, but there is a finite resistance between A and B. And that finite resistance is something that you found out here. This is the equation of your finite resistance, R on of the transistor. That you write down the equation of triode, find out what is VDS over ID. That gives you the finite on resistance of the transistor. So because of that finite on resistance, what happens is that you do not charge up or you do not discharge instantaneously. You take some time to charge or discharge. Why is that? Because if you have a resistance, so let's say you're charging up an inverter. So you have a pull-up network, you have a pull-up PMOS, and when the PMOS is on, that can be represented as a resistor. There is an on resistor in the pull-up network. And at your output, you have a capacitor. So you have a resistance and you have a capacitance. So you have an RC circuit. There is a time constant in any RC circuit. So it cannot charge. The capacitor cannot charge instantaneously. It will charge over some time. Similarly, when you're discharging, again, you're discharging through a resistor. Even though you're discharging through a short-circuited NMOS, that short-circuited NMOS has a finite resistance. So you cannot discharge instantaneously. The discharge will also take some amount of time. So that's what we are discussing here in this page. That if when you are charging, you will charge through this RC network, and when you're discharging, you'll discharge through this RC network. At the same time, because you have this finite resistance, which is basically modeled by the on resistance of the PMOS device, because you have this pull-up resistor, and you know that resistor is something that consumes power. Right? You consume power in a resistor. You do not consume power in capacitors or inductors, because capacitors or inductors, the impedance is imaginary. For a resistor, the impedance is real. Whenever you have a real impedance, you consume some amount of power in that, or some amount of resistive power. There is a concept of reactive power for capacitors or inductors. We'll not go into that. That is part of your electromagnetic theory. But here, it suffices to say that because you have modeled it with a resistor, there would be some amount of power consumption in it. What is that power consumption? That power is basically the voltage across this entire network multiplied with the current that flows through it over time. Now, you already know that the energy will be equal to an integration of that current multiplied with that voltage. And that energy, if you calculate this integration, if you do this integration, you'll see that the energy supplied will be equal to C times VDD squared. And the energy that is stored in the capacitor, again, that is high school physics. I'll not go through the derivation of how much energy you can store in a capacitor. You should know that the energy that gets stored in a capacitor is half C VDD squared. Half CV squared is the energy stored in a capacitor. So the energy supplied is equal to CV squared. The energy stored in the capacitor is half CV squared. Where does the rest of the half CV squared go? That gets dissipated in this modeled resistance. So this is sometimes called fictitious resistance because it is not a real resistance. It's the on resistance of the CMOS that you have as the pull-up network, but it results in some amount of power consumption. What is the power consumption? That is equal to half CV squared, because you supply half the full CV squared energy, but only half CV squared gets stored in the capacitor. The rest of the half CV squared is dissipated in this resistance. And again, you can do this integration to prove the half CV squared or the CV squared formulas over here. Similarly, when you are discharging the capacitor, the half CV squared that are stored in the capacitor will be discharged. So in a full cycle, when you're charging the capacitor, you waste half CV squared of energy because you are providing CV squared, you are storing half CV squared, and you waste half CV squared. When you're discharging, you're wasting half CV squared. So the total amount of energy consumed in a full cycle is CV squared. Okay, half CV squared during charging and half CV squared during discharging. And that's the energy. What is the power consumption? Power consumption is equal to frequency multiplied with energy. Basically, it comes from the fact that energy is equal to power multiplied with time. Right? So power is equal to energy divided by time. What is 1 upon time? That's frequency. So that's why dynamic power is CV squared F. Your CV squared was the energy per cycle. And if you multiplied it with the frequency at which you are charging and discharging the capacitor, or basically that is the clock frequency with which you are charging or discharging the capacitor, then your dynamic power becomes CV squared F. Okay. There is also this concept of propagation delay, and we'll prove how much is the propagation delay in the next lecture. We'll not do it today. So this is basically the proof of the propagation delay. But the concept of propagation delay is that, as we discussed, that you do not charge up instantaneously and you do not discharge instantaneously. During charging, it takes some amount of time. Again, during discharging, it takes some amount of time. The propagation delay, in this case, is defined as the time that is taken for the output to rise from 0 to, let's say 50% of the highest value. And while discharging, this is 50% of the lowest value. So this is VDD. If this is VDD, the point when it reaches 50% of the maximum, or VDD over 2, the time taken from 0 voltage. So at this point, it was 0. At this point, is VDD over 2. The time taken to reach VDD over 2 is called the propagation time for low to high. So when the output was low to high, how much is the propagation or how much is the delay that you have, that is determined by, or that is represented as tau p low to high. And this is represented as tau p high to low. So the time for propagation when it is going from high to a low. And again, from 100% to 50%, that's defined as the 50% propagation delays for low to high and high to low. There is also this concept of rise and fall times. What is meant by rise time? That how much time do you take for your output to rise from 0.1 VDD to 0.9 VDD? So 0.1 VDD to 0.9 VDD, how much time does it take? Why do you not consider the rest of the 10%? Because there could always be some amount of noise. right? And to take care of and you don't want to consider the noise in your overall system, right? In your system, you want to consider your system as ideal. So that's why you do not consider the rest of the 10%. You only consider when your voltage rises from 10% of the highest value to 90% of the highest value as the rise time. Similarly, the fall time is 90% of the highest value to 10% of the highest value. So that's your fall time. In the next class, we'll prove that the propagation delay tau p is 0.69 times R1 times C, and the T rise or T fall is 2.2 times R1 times C. So we'll prove these two things in the next lecture. Okay. And that will help you in solving some of the questions in homework number 9 as well. Okay, let's stop here and we'll discuss about some of these derivations in the next class, as well as the transmission gate logic.